Yeah, thank you. So in the previous session, we did look at what SVD is, and we came to a stage where we defined what is called as the cost function for the ratings prediction problem. And we said that once we manage to optimize that cost function, we would be in a position to predict ratings. That's where we stopped. What we're going to do today is I shall leave the floor shortly to Sandhya, who will take us through an example. So she'll take us through a data set, basically movie data set comprising of users and then movies and their ratings. She'll also take us through a bunch of codes and a package too that allows us to, or rather that will allow us to train the model and of course predict the ratings. Now in the process, of course, we'll not touch upon SVD because we are going to use the enhanced SVD algorithm. The reason why I'm using the word enhanced, not technically enhanced, it's probably inspired by SVD, because the algorithm that we're going to use is not technically a SVD, because SVD would assume that your matrix is not a sparse matrix. It assumes that all the data is populated. We did discuss in the previous session that when it comes to ratings prediction, you're going to deal with a sparse matrix where most of the entries could be question marks that you wish to predict. So SVD isn't the right algorithm there, because SVD by design assumes that all of them are populated. But the algorithm that we did discuss eventually was basically inspired by SVD. So what Sandhya would do is she'll take us through the code that will allow us to predict the ratings. And when it comes to optimizing the cost function using, when you optimize a cost function, you need a optimization algorithm. Let me put it that way. So of course we've heard of gradient descent. What we do in this case, given the large volume of data that we're dealing with, reasonably large volume of data that we're dealing with, we will be using an algorithm called stochastic gradient descent. And we will also touch upon a related algorithm called mini batch gradient descent. So that's where I shall leave the floor to Kayalvidi. She has a presentation ready. She'll take us through what exactly is gradient descent, stochastic gradient descent, and mini batch gradient descent, the differences. And she's got a bunch of interesting curves and surfaces that should help us understand the difference between these. And with that, we shall end the session, of course, leaving some time for questions. So what I shall do now is I shall leave the floor to Sandhya. Sandhya, over to you.
Okay. Screen sharing is disabled, I think.
One moment. Let me. Yep.
Hope my screen is visible.
Yep, it is.
So in this presentation, we are going to see about 3 important aspects in the recommender system. The first one is the package we are going to use, that is Surprise, and then how we are evaluating the recommender system, and finally the validation method we are using in our program, K-fold cross validation. And this is some introduction
if you don't mind, what is the problem statement here?
Yeah. This one is the problem statement. We are given a sparse matrix. We should predict the unknown values there. So our matrix will not look exactly like this. This is our matrix. I think the screen is still visible.
It is.
This one is the data set we are working on, which has the user ID, the item. Here it is a movie ID, and then the user's rating for the particular movie. And if you see the data points, the number of unique users in this column is 943, and the number of unique movies in this column is 1682. So we will get a matrix whose dimension is 15,86,126. But the data available here is 10,000, 100,000. So the matrix is a sparse matrix. It will look something like this. I guess it is still visible, right?
It is.
Okay. So our problem is we have to predict the unknown values in the question mark here.
And
So
what percentage of your matrix is,
sparse.
yeah, I mean, rather unknown? What percentage of your matrix is that? What, 90% is it?
93.6% in this case.
All right, okay. Go ahead.
And where should I start now? We see the coding part or the evaluation?
Briefly tell us what you're going to do, and then you can take us to the code.
Okay, we see. Why
So
surprise over cycle?
No, not surprise. Just tell us. So you have to predict the question mark, right? So what is the cost function that you're looking to optimize to predict the question mark?
Stochastic gradient descent.
No, the cost function. Stochastic gradient descent is the way to optimize your cost function. But what is the cost function that you're looking to optimize?
You're asking the algorithm I'm going to work on.
No, the cost function.
Cost function. RMSE and
No, that's the way you evaluate the algorithm. What I'm asking is a cost function, right? I think you don't have it here.
Yes, we see.
The sigma RUI minus PU dot.
Yeah, we see. I don't have that.
You don't have that, right? Okay, wait. Give me a moment. Let me see if I have it. Give me a moment, folks. I'll just share my screen for a short while before leaving it to Sandhya. Can you see my screen?
Yes, we see.
All right, so here we go. So in our previous session, we were discussing this. Here we go. So the whole idea is, if this is your matrix, you can reduce the problem to a rating being the dot product of two vectors. Think of these as latent factors. We discussed it in the previous, or other weights of the latent factors. So when I say latent factors here, it could be in the, in this particular world, it could be something like, say, an action fan or a comedy fan or romance fan, so on and so forth. And in the movies world, it'll be an action movie, comedy movie, romance movie, for instance. So the whole idea is you can determine the rating of a movie based on these latent factors. So think of PU as a vector. QI is also a vector. And of course, our UI is a rating, so it means it's a scalar. And what you're computing is a dot product of this vector and this vector. And what we're doing here is you have a bunch of RUIs that we already have. For example, in this matrix, you see 2, 3, 1, 1, 5, 1, 4, 4, 2, 3, 5, 1, etc. They're all, there's nothing predictive about them. Those are ratings that have already been given by users. So we make use of the ratings provided by users, and we figure out what is PU and QI based on this cost function. So we try to minimize this. So the whole objective of this algorithm would be to minimize this cost function, where we define the cost function as RUI is the rating provided by a user to a movie minus, think of PU.QI as the predictive rating. So think of RUI as the actual rating. This is predictive or estimated rating. You take the difference, square it, sum it across all the ratings that has been provided, which is in this case 2, 3, 1, 1, 5, 1, 4, 4, 2, 3, etc. Sum it up and then minimize. Right. So that's the, so Sandhya, so when I said the cost function, I meant this. So this is what you're trying to minimize, isn't it?
Yes, we see.
All right. And to minimize that, okay, now I'll leave the floor to you. You can continue from where you left. Go ahead. Share your screen.
Hope my screen is visible.
Yeah.
Should I move to the coding part PC or?
Okay, now you're going to solve this problem. So briefly, from a high level perspective, what are you going to do? Tell us. Or what you did. Tell us that.
So we have to split the matrix into two vectors, namely using the SVD algorithm. Namely, the one vector will have users, and the another vector will have the movies, and it is better to call that as a matrix, I think, column matrix and a row matrix. And each movie will have, say, 10 latent factors, weights of latent factors, which will, and each 10 will have some defined characteristics like 0.1% action fan and 0.2% drama fan. We saw that in the Friday session. We saw that in the Friday session. And this is how we are going to split the matrix and how we are going to predict
No,
the
sorry. Allow me to. So when you say split the matrix, what do you mean by split the matrix? I don't understand.
factorizing the matrix.
All right. So this is not
Yes.
splitting the matrix, right? You're talking of factorizing it.
Yes.
So which means you're saying in your code, you're looking at, or rather you're seeking 10, how many latent factors are you seeking?
10 factors is 10.
Okay, you're looking at 10 latent factors. It's an arbitrary number, am I right?
Yes, we see.
Or is there
We can
a
fix it to 100.
Sorry, say that again?
We can change that to 5
Okay.
or...
All right, okay. So you're taking 10. So which means you're looking for 10 latent factors amongst the users and 10
And
latent factors amongst the movies. All right. But what does that to do with mean absolute error? Why are you showing this slide?
this slide, we see this one. After splitting that into the latent factors, we will multiply the two latent factors. The latent factor of the movies with the latent factor of
No,
the
that's okay. But
user.
before that,
So
what do? You have your data set.
as we see,
Okay. So how many records are there in the data set now?
it have 100K.
Okay, 100,000. What do you do with the 100,000?
I will train the data set, split
Okay.
the data set and train.
Okay. So when you say split the data set, how are you splitting it?
I used K-fold cross validation here.
Okay. So when you say K-fold, did you use what was the value of K?
I guess it is 2.
Look at your code. How much did you? What did you do in your code?
2 VC.
2. All right. So explain what is two-fold cross validation. Forget K. Let's keep it simple. Two-fold cross validation. What does it mean?
First, what we will do is we will shuffle our data points, and then we will split the data points into 2 sets. I'm naming here it as set 1 and set 2. And then in the fold 1, I will choose the set 1 set of data point as training set, and set 2 set of data points as testing set. And then I will create a model. It will give me a result. I will evaluate with the model 1. For fold 1, I am naming a model which will be trained with the S1 dataset and tested with the evaluated with the test 2 S2 dataset. And then I will get one model. I will discard that after evaluating the RMSC and other
No,
uh,
don't
standard
jump into
deviation.
RMSE and all that. Why are
Okay,
you discarding? I don't understand. What do you mean by discarding?
I will not use that model anymore
Why?
because after these models are just for our understanding how it performs. When we are storing the model into pickle file, we are
No. Don't
the
jump into pickle and all that. We're not even
okay.
talking about pickles now. All right. We're not talking about serializing the model. Correct me if I'm wrong. So you have your validation. I mean, you have your data set which comprises of 100,000 records, correct?
SVC.
So you're doing two-fold cross validation. Is that right?
SVC.
Okay. So what are you going to do? You're going to split the 100,000 records into randomly into 2, correct?
SVC.
All right. So one set would be the training, the other one would be the validation, correct?
SVC.
All right.
And
So you train the
both
model. When you validate, what is that statistic that will help us to figure out, one number that will, at least in the way you've done it, that will help us figure out that the model is a good model or a bad model. What is that statistic in your?
that is root mean squared error.
Okay. Can you help us understand what is root mean square error now?
Okay.
Is that slide 11? Sorry?
We see even before that, what is the latent factor actually?
Okay.
It is
Later. Okay, go ahead.
like a characteristics. For a movie, we will have it is a rom-com. So it is a 10%, 50% romance and 50% comedy movie. So other 8 factors, say horror, action, drama, that will be 0. For if the movie name is something, if the movie ID is 111, it will have a latent factor. We will, ma'am, did you get that?
So latent factor means
let me put it this way.
The characteristics it defines.
Think of, see, you have some data, Srisha. Now, what latent factors? Okay, you understand what PCA is, right? Principal component analysis. So what does it do? It basically helps us unearth, shall I say, dimensions in the data, which you may not have seen. For example, let us say we are all wired in a way, let's say hypothetically, that all of us are either action fans or let's say comedy fans, or say romance fans. Let's say God has created us that way. Let's say, all right. And when we evaluate a movie, if I see an action movie, I'll evaluate 5 on 5. That's the way we are. Let's say I'm wired. Let's say all of us are wired that way. If I watch if I'm a say a comedy fan, and if I watch a comedy movie, then I'll rate it 5. Let's say again, this is all, let's say God decided. Now, in reality, what I'll do is I'll watch a movie and I'll give a rating, right? And I may be a combination of an action fan, a romance fan, and say
Comedy.
comedy fan, right? But I may not even know what, the percentage, as I say, all right? I may not even know that, okay? What I do is I just rate movies, and everybody is going to do the same thing. Every user is going to rate movies. Now, what we're doing here is we're taking the ratings data and we're trying to look for these dimensions. So when you run PCA, SVD, any of those dimension reduction algorithms, what it does is it manages to unearth these dimensions from the data. So at the end of it, it'll say, look, given this data, I see 3 dimensions. Of course, it will not tell you that dimension 1 is action, dimension 2 is romance, dimension 3 is comedy. It can't say that. But it will definitely tell you that there are 3 dimensions in this data set. All right. Now, these are called latent factors. These dimensions are called latent factors.
Okay, got it.
So what Sandhya has done in her code is she has restricted the number of, again, when you have a huge data set with a lot of columns and rows, you can have a lot of latent factors. But the reality is such that you don't need so many latent factors to explain the rating. All right. So for example, let's say, I'll give an example. Let's say I'm an action fan. Let's say I'm 10% action fan, 50% comedy fan, say 49% romance fan, and I'm a 0.01% Rajini fan, 0.03% Kamal fan, 0.05% say Surya fan, so on and so forth. And let's say everybody is like that. Let's say all of us are such that, it's action, comedy, and romance that dominates our ratings, and not Rajini, Kamal, Surya, Mahesh Babu, blah, 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 right? So the point that I'm trying to make here is, even though Rajini, Kamal, Surya, Mahesh Babu can be a latent factor, they don't dominate your rating. So you can have, say, 100 latent factors given the data set, but typically you will find that a few latent factors would dominate the rating, right? So when you run the SVD algorithm, you find out those dominant factors. That's where the eigenvalues come into picture. You sort it by descending order of eigenvalues, and you take the top few eigenvalues, and you come to a conclusion that those the latent factors represented by the top, in this particular case, 10 eigenvalues is sufficient to explain our rating for a particular movie. All right. So what Sandhya has done is she has stopped at 10. So she has gone with the assumption that 10 latent factors is sufficient to explain the rating that a user gives to a movie. Is that clear, Sarisha?
Yes, VC. Yes.
All right. Sandhya, over to you.
So where should I start?
All right.
with the
So okay. So
evaluation methods.
yes. So okay. So you've taken the test. I mean, you've taken the test data or other training data. I don't want to use the word test. Training data. Then you're validating it. All right. So my question was, while validating it, what metric are you going to use to measure the efficacy of the model?
Here I'm using two metrics, evaluation metrics. First one is mean absolute error, and second one is root mean squared error. And
What's the difference?
in mean absolute error, we will have the predicted value predicted by our model, and we will have the actual value in the test set. We will take the absolute of the difference between these two, and we for the entire data points in the test set, and we will divide that by n. The n is the uh, total number of data points.
Again, when you say total number of data points, that's a bit vague. Is it the total number of points in the validation set or training
I
set?
guess it is total number of points in the validation set.
All right. Okay. So that's your mean absolute error. And then the next one?
Mean root mean squared error is nothing but we gonna square the.
No, that's the next slide, right?
Okay, let's see. We will square the difference between the predicted value and the actual value, and divide that by the total number of data points in the test set, and we will take the root of that.
So you square and then you sum, right?
Yes,
You
we see.
square, you sum, and then you divide it by the total number of data points. And then finally you take the square root, correct?
Yes, we see.
All right. Okay. So you're going to do. So question, you're doing twofold cross validation, correct? So
Yes.
let's forget mean absolute error. Was it mean absolute error, the previous slide? Slide
Yes,
number
yes.
7?
Yeah.
Okay. So let's park that aside. Let's just focus on root mean squared error, RMSE. For twofold cross validations, how many RMSE are you going to calculate?
2 we see. For two
Okay.
models, I will get 2 models.
Is it 2 models? Think about it.
The articles I read said that we will, for n-fold cross, for k-fold cross validation, we will get k different models. The
No,
first
no,
model
K,
will be
no, no. Is it K models or K different folds? Think when you develop a model,
SVC.
what do you use to develop a model?
I will use some algorithm.
Okay. So okay, so what you're saying is, correct me if I'm wrong. So you use a training set, develop a model, and then you validate it. Okay,
Yes,
so that's one model according to you, right? Then
yeah.
you flip it, is it, in case of twofold?
Yeah.
Okay, all right, all right. Okay, go ahead. Okay. So you
I
calculate the
thought
root mean squared error.
if we use say same model for the second data set also, it will be already experienced the data set which it gonna face in the fold 2.
No, but don't you see that it will get trained using a different data set, right? Correct? Right.
Yeah,
So
we see,
in
but
a way, it is a different model, isn't it? Because the parameters that shall be, I mean, the weights that shall be derived will be different, isn't it? Correct?
yes, we see.
Between, so you have one training set on the basis of which you train the model, which means at the end of it, you'll have a bunch of weights, correct?
Yes, we see.
You use those weights on the validation, you use the weights in the model, of course, on the validation data set, and then you figure out RMSE. Now you you flip it in the sense, what was earlier the validation set is now the training set. I'm sorry, is the training set, correct?
Yes, VC.
Now you will get a different set of weights. Am I right?
Yes, VC. The weights will be changed.
Weights will change. So the model is a different model then, correct? Though the
Yes,
model class is the same. You might be using SVD, for instance. So from a class of models perspective, both are using the same class, but the model is a different model. Why? Because when you train it using a different set of data, you will get a different set of weights. Am I right?
Yes, VC. You're right.
Okay, and then you calculate RMSE. All right. So let's say you basically you have two RMSEs now, correct?
Yes, VC.
All right. So let's say you have two RMSEs. Then what? Let's say you're happy with both RMSEs. What do you do then? Next, because you have two models now. Which one do you end up using?
I will train the model to the through the entire data set. Pickle file. I will save the pickle file.
Sorry, say that again.
I will have. I don't get how you are saying I will get two models, and after that I will.
No, the reason I'm saying is because I may be wrong, but correct me if I'm wrong. Okay. I have a training data set. I have a validation data set, correct?
Yes, VC.
I run an algorithm to, on the training data set to train and get the weights. Then I apply the weights and the model, of course. On the validation data set, I get an RMSE. Then, of course, at the next step, I flip in the sense, what earlier was the validation data set is now the training data set.
Yes, VC.
So don't you see that the weights would have changed? Need not be the
Yes,
same,
yes.
right? Correct. Then I get a different RMSE. Now, don't you see that in the first case, I have one set of weights. The second case, I have another set of weights.
Yes, VC.
Which one am I going to use? If I have to make predictions, let's say,
Predictions on the unpredicted data, that is the question mark. He will train the model with the entire data set. VC.
so what is the purpose of K-fold then?
It is just to evaluate the algorithm, how good the algorithm at predicting data points and targets.
Naveen, just your point of view. What is the purpose of K-fold? Let's take twofold, for instance.
How will the model get trained for unseen
Okay.
values?
All right. Okay.
It's
I think
for the, VC, I think the intro class
Sorry,
back-
Sandhya's answer, I'll go, Naveen.
Yeah.
Sandhya's answer is correct, VC. So she's bang on. So the purpose of K-fold is to, we talked about this in one of the first few sessions.
Mhm.
We want to understand generalization error. I want to know that when it's very expensive to go in real life, in production setup and understand the errors. On the other hand, given my data, I will be able to understand that if this is what the real life setting is, what will be the error that I will see. So we split the data and then into multiple folds. In each one of the times, I'm going to use a different fold as my validation data set and see what the error is. Because one of it could be totally out of whack, maybe too good or too bad, we use K-fold to ensure that we average and see what, on average, what the error looks like. So the understanding is that will give me some understanding of the generalization error in real life. When I go live, what is the kind of error that we will get, with the strong assumption that the kind of distribution of data in production mimics what kind of data that we have when training. So that's one where K-fold cross-validation allows, gives you an indication of what the generalization error is. Now, when we go into production, as Sandhya told, why leave something out, right? We have the entire data. We'll go build a model on all the data set, and there's only one model that we take and deploy in production. So when you build, you get both of these things out of the box.
All right. So question. So when you say build the model, so which means when we are computing the weights, for instance,
Correct.
we will use the entire data set, is it, to compute the weights?
Correct. Correct. Yes.
Oh, so at that
Everything
stage,
is-
we're not going to again have one training and
so doing
validation.
k-fold cross-validation, you will use the entire data set. If you explicitly split into a train and a test, then only the model comes only from the training data set.
But let's say I've done my k-fold cross validation. I'm done with that. I'm happy with, let's say in each fold,
Mhm.
I managed to compute a root mean squared error, and I'm happy with the RMSE. All right.
Right.
So now I need to figure out one model that I can use and move it to production. Right. So my question is, would I train the model on the entire data set now that I'm happy with the root mean
The
squared
library
error?
does it out of the box, but that is correct. Yes.
Oh, all right. Okay. So it takes the entire data set and then trains the model to compute the
Correct.
weights. All right.
Correct.
Okay.
That
Okay.
is right.
Cool. Okay. Got it.
But
Yep.
it is computationally expensive.
So good question, Abhinav. So there's we have to invoke some probability. There's this concept of law of large numbers. Okay. So read more about it. I'm not going to explain that here. But if you have lots of data, and when you deal lots, say I have 100 million data points, then I don't need to do k-mean. I don't need to do k-fold cross-validation. 80-20 split or a 90-10 split is good enough for me to build a model. On the other hand, when my data is relatively medium size, say 100,000 to 1,000,000, that's the point when I know that I don't have lots of data, but I also don't have less data, which means that there is a variability that I could see, and I want to characterize my variability, which is what is known as the generalization error. When you have 100 million data points, you're probably at a level where you've understood the models won't vary so much more. Going from 100 million data point to a 200 million data point, your models may not change so much. On the other hand, when you go from 100,000 data point to 200,000 data points, your models can entirely change. So that's at that level. So that's why we want to do k-fold cross validation at that level, and it's also not computationally too expensive at that time, right? So if your models the data is huge, then it's going to be computationally expensive. Generally, k-fold is done when the data size is reasonably limited. So say 100,000 to 1,000,000 is generally where you would do k-fold cross validation. Make sense?
Got it, Bhargav.
All right. Sandhya, go ahead.
Okay, then
Okay. Then take us through.
the code.
Yeah. Before that, which package did you use?
Surprise.
All right.
It's
So what's the price?
So we have in Scikit we also have a scikit-learn, but we are not going to. We have used that for training the other machine learning models like regression, classification, and here we are not going to use scikit-learn since it is since that we have a data set which in matrix form looks something similar to this one. And here we have a data set which in the matrix form will look something like this. So it is not a good practice. We can't, in recommender system, we can't get something useful from the scikit-learn packages. So here are the few purpose of using Surprise package. Sorry. First one is dataset handling. It has some built-in datasets for movie rating prediction, and then it has some prediction algorithms like SVD and matrix factorization algorithms, and similarity measures like cosine and Euclidean distance measure. And it also have good tools to evaluate the algorithm, that is the cross validation.
All right. So who came up with this package? Surprise.
Nicholas Haga.
All right. Okay.
He did when he is doing his PhD.
All right. So is it still active? I mean, people are using
Yeah.
it, is it? Okay. All right. Good.
I think I'm done with the PPT. Please.
Okay. What is this future possibilities? What are we?
Yeah, if we successfully build a recommender system model, we can deploy that. We can develop a front end program to make it available for the users.
Okay.
And then we can also, with the data available, we can show some descriptive flow charts describing how many times we have watched a particular movie, or how many movies we have
So
rated.
you mean descriptive statistics, right?
Yeah, yes.
Okay. So does that require a machine learning model?
No, we see, but with the available data, we can do that and put that
So,
in our website.
all right. So you're saying that you can have a solution where it can throw up descriptive statistics as well, and it can also do predictions. Is that what, or it can do something on top of predictions? Is that what you're trying to say? Both. Right?
The surprise model will not do. I
No,
don't think the
not
surprise.
surprise. I'm talking of your
But with
future
the available
possible.
data,
No,
we can perform.
I'm talking of the future
descriptive statistics.
possibilities. I'm not talking particularly about surprise, but
Yes, we see.
all right. Okay. And what is this API development?
API development is for we can get data from other sites and use it for our site for get an accurate rating.
Sorry, I didn't understand. Say that again.
Like we have a website which will show the Rotten Tomato rating and IMDb rating. So we can get the API of Rotten Tomato website, and we can get the rating of IMDb website, and we will get the mean rating and we can post it in our website.
How is
Any
that
thoughts on
API
that?
development? You're using someone else's published API, correct? How does that become API development?
Okay.
I think what you meant is using your data set, you can offer endpoints. Is that what you're trying to say? So it's like a user can come in and then you'll offer the user an API that will allow the user to say retrieve a predicted rating, maybe top 3 recommendations and all that using the data set. Is that what you're saying when you say API development?
Yes, VC. I think I didn't.
VC, I think she has mentioned, right? So I think she's been telling we can use this into production via API. That is what the
Right.
context
Yeah,
is,
I
right?
think so. Yeah,
That's
correct.
nothing with like this particular package or this use case. Like it's just you can use it like wherever you want. That's it.
Okay. All right.
Not stick to this API database management front end. That's okay.
Okay, go ahead.
It's a part of application development, not a part of this thing.
Okay. Go
Okay,
ahead.
VC,
Yeah. Show us what you
VC,
have.
that's the code. You want me to show the code?
Yeah, sure.
Okay.
Go ahead.
Hope my screen is visible.
Yeah. Can you show us the data? Do you have the file with you?
As we see.
Can you
Yes, VC. I'm trying to do that.
can you compress it? It's easy. Okay, wait. You probably haven't used Excel before, right? Okay. So what is column A?
Column A is user ID.
Column B?
Column B is movie ID, and column C is rating for that particular movie.
Okay, so that's the data set on top of which you train the model. Go ahead. Okay. Go ahead with the code. Yeah.
SVC. So,
Are you sharing the code? We can't see it.
okay, Lucy. Wait a minute. Now, I hope my screen is visible now.
Yep.
And we are importing some libraries, and then we are using an algorithm called, we are defining an algorithm which is matrix factorization. This block of code will do the matrix factorization work. It is easy to factorize a dense matrix which has all the data present, but it is not that much easy to factorize a sparse data. So here is an algorithm
Is it not that much easy, or can you not factorize at all?
we cannot factorize
All right.
this one.
Okay. All right.
So here the author Nicholas has came up with a program called came up with a class called Matrix Facto, which will split the user into its characteristics, that latent factors. Like I told earlier, how much a movie can be split into action, drama, and comedy, and so on. And then after splitting the data into, here we are splitting the data with splitting the data as a user ID and items. And then we are passing it through stochastic gradient descent to get the minimum error possible. And then we are passing the vectors, the user vector and the item vector to the SVD model. After passing through the SVD model, we will evaluate the algorithm's measure. First, here we are going to use two algorithms. The first one is SVD and the second one is K nearest neighbor. So SVD gave us an root mean square error. Root mean squared error as 0.9845 and 0.9864. And for these two values, the mean and standard deviations are calculated. I think I have. Sorry, this one is 4. This one is for the matrix facto algorithm. This one is the SVD algorithm. And then we are also doing the same for the k-nearest neighbor algorithm and comparing the three algorithms.
What is this matrix facto algorithm? What is the difference between? So this is KNN, right? Okay, neighbors, all right.
SVC.
SVD is fine. What is a matrix facto algorithm? We never really discussed that. What's that?
This part of the code we see.
No, you said the three algorithms.
This is the
right?
matrix facto we are passing. In one PC.
That's the optimization, isn't it? Correct? SVD optimization, correct?
SVC.
So no, keep it simple. How many algorithms are you testing here? How many?
2 we see.
Okay, which ones?
SVD and K nearest neighbor.
Okay, simple question. Which one are you choosing? K means
The
or
which
so
one,
is it K?
the one
Sorry,
with the
K
least number
nearest
of
neighbors, right? Sorry, what is that? KNN is K nearest
K
neighbor.
nearest neighbor.
Okay, any particular reason why you decided to compare two models? I mean, two algorithms?
Sorry, VC. I didn't think about that.
All
I
right.
saw
Okay,
the
fine. That's fine. Okay. So you basically you took two algorithms. So one was SVD. Again, that's technically not SVD, though we are calling it SVD, right? Okay. Other one is K nearest. Is it K nearest neighbors? Am I right?
SVC.
All
K
right.
nearest.
Let's not talk about it because we haven't talked about that algorithm before. All right. But still, you ran the data through that algorithm, and then which one did you choose?
I choose SVD over KNN
Why?
since the root mean squared error of KNN is quite larger than SVD's root mean
All right.
squared.
Show me the RMSE values for Canaan.
This
Okay.
one,
So 1.0012. And what do we have for SVD?
0.95.
Okay. All right. So you decided to choose SVD, right? Now, question. The so-called SVD algorithm, we discussed in the previous session that it's not quite SVD, but we are basically figuring out those PU and the QI vectors that we discussed, right? The weights. And we minimize that cost function. So how do we minimize that cost function? What optimization algorithm is this code using to minimize the cost function?
SDGVC. Stochastic gradient descent.
Okay, stochastic gradient descent. Okay. I'm not going to stop here now, but after you finish, I would want Kyle Vidi to talk about what is the stochastic gradient descent. Okay, we'll come to that. Anyways, so proceed. Go ahead.
So after evaluating these two models, SVD and the KNN, we are particularly evaluating with some values, the user ID and the item ID, here movie ID.
Okay, so,
So
when you say evaluating, so you're trying to
get the I will give a user ID and a movie ID, and the model will give me the rating. If the user has seen the movie, how much will he rate for the movie?
Okay, show me. So when you run this predicted rating, so you've given the user ID as an input and the item ID. Item ID is a movie, is it?
SVC.
All right. Okay. So what do you see there? What is R_UI and EST?
It is the action we are passing the rating to, and we are comparing it with the this one is the actual rating predicted by the model. This one is the rating we pass, so it should give us an error. I think here I have compared the estimated by the model, the estimation. If
Okay.
I pass the movie
I-
ID as
Sorry, I have a
6
doubt.
and use.
Sorry
Hello?
to interrupt you. I have a question here. Yeah, VC, maybe for you. Are we still in with collaborative filtering? Is this collaborative filtering?
It is.
Okay, so okay, can you explain like maybe in a word or two? Like maybe I don't like I didn't get it. Maybe some of the people out here also may not get it. I just want to explain in a simple terms on a day-to-day our use case, like what is collaborative filtering and can we apply that?
collaborative filtering usually deals with the user and the content. Here the content is movie.
Okay.
It will compare, excuse me.
Yeah. Go ahead.
Yeah, with the available with the what we will do is we will some user correct me if I'm wrong. We say a user 1 and 2 has seen same movies and
Okay.
rated are almost same for the two movies for a certain set of movies. And we have a movie, say M5, which the user 1 didn't see, but the user has seen and rated. So in collaborative filtering, we will predict how much the user 1 will rate for the movie 5, which with the data his neighbors, that is the user 2 has seen. Since
Okay.
I'm calling it, he is a neighbor since they share a same taste.
Okay, so let
movies.
me put it this way, like while you're purchasing Amazon, like if you order a, let's say you're purchasing a mixie, then you will get a jar with it. Like there will be a recommendation for a jar. So
Based
reason
on
that,
content, that is recommendation based on content.
the reason that because most of the people who purchased mixie has also purchased jar. Okay, so these are the similar set of use case, like similar set of people. So what my collaborative filtering model will do, okay, since like you user, you fall under one particular category, let's say me and you, so we both are in one category. You purchased mixie with jar, I purchased only mixie. So the collaborative model is telling that, okay, since Sandhya has purchased a jar, why don't you consider it as an option? So like from your output, where can I visualize the nearest neighbor, right? So how can I visualize that? Now you're giving an input, you're throwing an output. Okay, that okay, like yes, from a model point of view, that is how it works. But how
Yes.
can I visualize through a process telling that, okay, so where is my KNN plot? Where is, let's say you're telling you're giving some rating, but what is the definition behind rating? Can you put it in a plot, tell that, okay, since because this user fault here, that is the reason why I've recommended this. Like what I do think only then you'll be able to understand like how it works. I don't know, like that is our thing. Maybe if we see if we have anything.
No, I don't know. Were you there in the previous? Were there on Friday? Were you?
Oh no, I was not there on last.
Okay.
Class.
Yeah. We actually discussed
Okay.
collaborative filtering. So wait a minute. See, this is what we talked about. Give me a moment.
Yeah.
Can you see my screen?
Yes, got it. Okay.
All right. So this is what we discussed
Okay.
in the previous session.
Yeah. So what I mean is, let's say if you can put it in a visualization while doing in a code, right? Say so you have a model. Like I thought, okay, if she can put everything on a graph, let's say user is here. So this is why the rating, the reasoning, like some kind of intuition behind it. Will that
But
help?
but question, I mean, given the volume of data and given what we are doing, we are actually doing matrix factorization. I'm just wondering, whether it's and there are 10 dimensions.
But yeah, you can represent in like 2 dimensions using you're doing dimensionality reduction.
Yeah,
Just
after doing the reduction, we have about 10 dimensions. So I'm just wondering, is there a way to?
yeah, you can reduce it to 2 and plot it, right? And you can see where the user falls.
Okay. Yeah.
Some kind of intention, like
So
I think that will allow you to think beyond dimensions.
Fair point. Yep, I agree.
So I have one small clarification. So Instagram is collaborative filter, if I'm not wrong. So YouTube is content based. So
No, right.
am I
So
right?
in YouTube also it will shows, okay, this particular channel viewers have watched this channel.
No, that is now recently YouTube has updated, but before they were only listing the contents what we are typing.
No, I'm not sure. Like I have to think through this.
Naveen,
There,
if anybody have recently watched Netflix, so
Mhm.
there you will see that visually, right? If you have watched a movie, you will also like this. Or
Yeah, yeah.
so many of them have, yeah, viewer of this have also watched this.
Yeah.
So
So
that's
like
one of the,
whatever the
yeah.
yes, Pradeep, exactly. So whatever the recommendation system I see, it will be the combination of few things, right? It will not be collaborative filtering standalone. Like it will be the combination.
Yeah, yeah,
So
right. Yeah, we spoke
when
about
you
that.
when you say combination, what do you mean?
so combination, I mean, like if you see Netflix, right? So you have two sections. One will see, okay, you have watched, your viewers have watched this, your set of viewers have watched this movie and they like this, so watch this. This is collaborative filtering there.
Hmm.
Two is, let's say, if I like Tamil movie, they'll suggest only Tamil. That will be in one category. So that is based on my preference, like irrespective of what other user tells, right? So if I have a fan base for a particular hero or a comedy, and then I used to get that see like regularly. That is one, like it has multiple sections where each section can represent a type of recommendation. One can be on popularity. So
Hmm.
stuff like this, I think YouTube mixes everything, if I'm not wrong.
All right. It's not merely collaborative, is what you're saying,
Yeah.
right? All right.
Okay,
Bhargav.
I have a question. Sorry, I think of all the people, maybe either Sandhya or VC. Can one of you really explain what collaborative filtering does? I mean, I did listen to the previous session, but I still am confused. So,
Okay. Sandhya, would you want to go or would you want me to
like,
go?
please, okay, too late. I've had a very, very, very long day. So please, no mathematical jargons. I want it like you're going to explain it to my kid. How would you do it?
Yeah.
Collaborating. So collaborating filtering is based on the previous users, what they had consumed a lot. Based on it, the recommendation will be done for us. Whereas in content based, the contents
No,
consumed.
don't break
mix
content.
topics. Don't mix topics, please.
Okay.
I only want to know. Please explain
So
what
that's not
collaborative
collaborative
filtering.
filtering.
Like what? No,
So
how does
what
it
the
work?
mostly
Correct me if I'm wrong.
Yes, Sandhya, go
So,
ahead.
I think I'm repeating the same example where, yeah, say there are two users, they mostly share same interest on movies. Like they are action fan, and recently there is a movie called Movie One. The user two has seen the movie, but the user one didn't see the movie. So it will recommend the user two. User one is recommended based on the ratings given by user two for the movie which is recently released. If he is rated so high, uh, it will recommend that to the user one. It will not take only one as a neighbor. There will be many neighbors for a particular user. The neighbor in the sense is a group of people who share a particular interest. Say they are a group of action fan or a group of comedy fan. Am I wrong, Bhargav?
I'm listening. No, you're okay. Go ahead.
I think if the particular set of users has rated the movie not so movie as bad, it will not recommend the movie to the user one. This is what happening in the collaborative filtering.
How does it work?
How does that it work?
So I think first step is to identify, if I'm a user, I think the first step is to identify who's close to me, the set of users who are close to me, my neighbors. I think that will be the first step. Of course, the way to do that is I'll have to identify, I mean, in the case of movies, I'll have to identify users who have rated the same movies that I have rated. That's the only way to identify who are close to me. Then I have something called as you have to wait. You mean you need to devise a way to define what is this closeness. So you have something called a similarity measure that will help us define the closeness. And once I've defined my neighbors, now I know who my neighbors are. And if I take a movie that I haven't watched, then the whole idea is I'll check my neighbor. I mean, the algorithm would look for my neighbors and say, okay, your neighbors have rated this particular movie, say 5/5. So I'll recommend this movie, something like that.
We see, for 1.5 years, we didn't discuss any of this, no?
No, all this was discussed in the previous session.
No. Now, the algorithm that Sandhya walked us through didn't have any of these concepts.
It didn't because we're not using this algorithm.
I asked explain collaborative filtering. We are listening to collaborative filtering, and
No, it doesn't, because what it does is it identifies latent factors, isn't it? Which isn't quite as simple as what I explained now. It doesn't identify neighbors.
what is the impact? What is the role of matrix factorization here? What happens? Which is what you covered in the last session, which is what the code also covered today.
Correct.
Happens there? Like, why do we need matrix factorization?
It identifies, again, I mean, I'm just thinking of how to put it in layman terms.
It's okay, then explain whichever way you want. We will.
All right. So, I mean, there are a bunch of movies, there are a bunch of users who've rated them on a scale of, say, 1 to 5. What matrix factorization allows us to do is it identifies dimensions into which I can, categorize users and movies. Something that may not be evident initially. So, I mean, as I said, right, let's say God decided that we are all action fans, romance fans, and then comedy fans, 3 dimensions. Of course, we don't know that, but our ratings, once we give ratings to movies, matrix factorization will allow us to figure out that there are 3 dimensions in which we can categorize ourselves, 3 independent dimensions, say action, romance, and then comedy.
Okay.
And once I'm able to, so what it does is it does this for both movies as well as users. So in this case, there is an interaction between movies and users. So what it does is it categorizes users into 3 dimensions. I'm assuming 3 here. It can be more, of course. And then users into 3 dimensions. Users and movies in 3 dimensions, say action, comedy, and romance. And what it does eventually is it allows a user to be defined as a linear combination of these 3 dimensions, and a movie as again a linear combination of these 3 dimensions. So when these 2 interact, when I give a rating, for instance, what happens is, if I'm an action fan, if it just turns out that I'm a dominant action fan as compared to being a comedy fan, and if the movie turns out to be an action movie, then of course my rating would be high.
Fair point. Yes.
Right. And likewise, if I turned out to be a comedy fan, if the movie turned out to be an action movie, my rating would be low. Right.
Right.
Again, I'm using the word action, comedy, etc., just for the sake of.
Yeah, I understand. So that we all understand something around it.
Yeah, it is called latent factor, whatever it is. Right. So what matrix factorization allows us to do is, it just allows us to, with this matrix of users and movies, it allows us to figure out various dimensions across which or identifies various dimensions that may not be
Yeah, how does the
evident.
learning happen? So I know what is the learning here?
Matrix factorization. Okay, well, when you're factorizing a matrix, okay, let me put it this way. I'm not sure whether you can call that learning, but let us say I can, given a data set, I can figure out, say, 20 dimensions, let's say, right? What matrix factorization will allow us to do is, it'll allow us to figure out the dominant dimensions that can explain my behavior. So in this case, the behavior is my rating for a movie, or rather all the ratings of all users for various movies, right? So matrix factorization what it does is it produces all dimensions, and then what you can do with that is, technically, that's what we discussed in the previous session and in the SPD session, where we talked about ordering it by the eigenvalues, and we pick out the dominant eigenvalues. So let's say in our world, there'll be 3 eigenvalues, for instance. Action, comedy, and then I don't know whether to call that learning. I'm not
correct. So there is there's a gap in understanding. That's what I wanted to bring it out. No, you fully understand the entire math of it. Okay. But there's a gap in understanding of this word learning over here, which is what I want to discuss, because I saw that in last week also, but I joined this meeting late and I got an office call, so I couldn't come to you, explain this earlier. Let's understand. This is all okay, but okay, Kanmani has written something. Can you explain what this is, Kanmani? I'll give you a day off if you can explain this.
Thanks, Varga. What the collaborative filtering is doing in the recommendation system is, so based on the previous user preference, based on the similarity between 2 users, we can predict the future reference of the user 1 by using the latent factors. Like latent factors here is the hidden futures of the type of the journal they want.
But this one still doesn't tell how learning happens. No.
Can I take another stab at it?
Go for it.
Let me try.
You're not leaving until we all understand this really well. This is important.
Okay.
Because I clearly understand you. All of you understand matrix factorization really well. All of you understand recommendation system, collaborative 15 really well. You guys are not making the connect well.
Learning. Okay. I'm just trying to put it in layman terms here, from what I understand.
Yeah.
Okay, let me just share what I had from the previous session.
Yeah, sure.
All right. So forget all this. This is all matrix factorization. We don't want to talk about it. Now, this is the problem that we're dealing with. All right. So what matrix factorization allows us to do is, it allows us to reduce the rating prediction problem to basically dot product of 2 vectors, PU and QI. Imagine PU to be a linear combination of latent factors, and QI to be a linear combination of latent factors. This, of course, is users, and that, of course, is movies. Yeah, movies in this case. That's right, items. Now, what we are doing is, given the existing ratings that we have given, users have given to movies, we make use of these ratings as demonstrated by, I mean, as represented by this variable RUI, which represents
Hmm.
the rating given by a user to a movie.
Mhm.
We try to estimate PU and QI.
Hmm.
So PU here is, as I said, one way to look at PU is look at all the factors, or
Hmm.
we decide, let's not look at all factors. We'll probably pick the top 10, something like that. Okay. And QI, which has to be estimated, because
Okay, let's assume so PU and QI, right?
correct.
Okay.
These are vectors.
No. So let's do P. So there is a rating matrix R.
Mhm.
R is equal to P times Q, right?
Mhm.
What is the dimension of R? Take some dimension. What is the dimension of R?
So in this case, let's say 1, 2, 3, 4, 5, 6 cross 5, right? In this case.
6 cross 5 is R. What is the dimension of P?
Uh, P can be, it can be 1, it can be 2, it can be 3, it can be 4.
It's okay. Let's assume.
Let's say it's 3. Let's say it's 3.
What does the number 3 here mean?
Which means I am looking at, if I decide it's 3, then it
So
means that
there are 3 latent factors for
that's
the.
right. Correct.
That's what you're looking at. And
That's right.
remember, that's a hyperparameter over here.
Correct.
Okay.
Yes,
Remember
it depends on when I do the matrix factorization. I mean, it depends on the eigenvalues. Of course, we're not doing matrix factorization here, to be very honest. We're just using the
Correct. That is
principle.
why we'll differentiate. We'll only solve this first before we. Okay. So here you're assuming 3 to be the latent factors, and if it is 3, what will be the dimension of P?
Wait, it would be 1, 2, 3, 6 cross 3.
Okay, and Q will be
3 cross 5.
Okay. So this is correct. Anyone has any question on this? Is everyone on understanding this? So we are assuming that there are 3 latent factors. The rating matrix is of dimension 6 cross 5, which means that P and Q would be 6 cross 3 and 3 cross 5. Anyone didn't understand? If you don't understand what we build on this, will be harder. Everyone understood this? Yes? Okay. Yes, we see. Continue.
All right. So now,
Okay. Mhm.
of course, PU is a vector and QI is a vector, of course. Each of, I'm not sure whether I'm using the right term there, but I'm calling it dimension. Or let me put it this way, there'll be three elements in each of these vectors, PU vector and QI vector, right? I'm supposed to estimate these values. So the way I'm doing that is, let's assume PU and QI, I mean, I have to start with some initial assumption for the value of these 3 elements for PU and QI.
Why only 3 elements? Can you come back again? Why 3 elements?
That's because the dimension of PU, and if you look at the matrix, right, it's the whole P matrix is
PU is
6 cross. PU is one row. Imagine one row.
Correct. PU is one row.
One row.
Okay.
That has three elements there, right? Because this is a 6 cross 3 matrix.
Correct. Yes.
So, and likewise, QI is 3 cross 5.
Correct.
So what you're doing is you're multiplying. So you'll have 3 elements here and 3 elements there. Now you'll have to estimate the values for these 3 elements, right? So you start with an initial assumption for these values. But before we get there, what you're trying to do here is, assuming that you have a PU and a QI, let's assume, you can come up with an estimate or rather estimate of the rating, which is basically the dot product of PU and QI, right? That's this. And I can figure out the difference between, of course, what I'll do is I'm not going to look at the question marks because those are ratings that I'm supposed to predict. So let's neglect the question marks.
Mhm.
So let's say I pick this number 3, the one that I'm highlighting here. All right. So RUI would be 3.
Mhm.
PU would be a vector. QI would be a vector. I'm estimating those vectors. I'm calculating a dot product, squaring it. I'll do this for every single
Done.
element that
Mm.
I mean, for the sake of discussion, I'm not splitting it into training and validation and all that. Okay?
No, it's okay. Sure.
All right. So I take all the data elements here. So let's say 2, 3, 1, 1, 5, 1, 4, everything, right? And I'm going to minimize this.
Mm.
So now when I'm going to minimize this, I need a way to optimize this
Mm.
function to minimize, right? And that is where I would end up using an algorithm such as, say, stochastic gradient descent, which will allow me to, of course, I could have used gradient descent as well. Nothing stops me from using that, but there are pros and cons. That's a separate discussion in itself. Why gradient descent, why stochastic gradient descent? That's a separate discussion. But let's say for the sake of discussion, we are using stochastic gradient descent.
Mm.
So what I'll do is I will minimize this function using stochastic gradient descent algorithm, which would involve figuring out partial derivatives of P's and Q's, and then going down the that surface to figure out the minima. At the end of the whole exercise, I would have figured out all my PU vectors and all my QI vectors. So which means there are, say, 1, 2, 3, 4, 5, 6 PU vectors, one for each user. I would have figured out all my QI vectors, one for each movie. Now, once I've done that, given the way we are estimating the ratings RUI, which is nothing but a dot product of the user vector and the movie vector. Of course, when I say it's a vector, it's a linear combination of latent factors, right? I can estimate the rating. So I'll have all these question marks calculated. Of course, when it comes to training, I would split.
Sure, that's okay. Sure.
That's a different thing.
Understood. Understood. Yeah.
So that in a nutshell is what we're trying to do here.
Okay. This is correct. Is everyone clear with this approach? It's not so obvious with the code.
Now, which is why, I mean, we knew that it would not be very obvious with the code, which is why we did the entire previous session was to drive home this point that this is what we're attempting to do. It's just that we stopped with the minimization function. We didn't talk about how we go about minimizing the function, which is where stochastic gradient descent comes into picture.
Why is stochastic gradient descent and not gradient descent?
All right. Okay, Kyle, can you share? You have something to share. Can you?
Yes, yes.
Go ahead.
Okay, in surprise package, this is literally 2 lines of code. So
that's right.
So understanding why this happens is super important. Okay.
Okay. So Kyle,
Yes, yes.
take us through that do you have that surface with you? If you don't mind,
Yes, yes.
show
I
me
can
that.
share that.
Yeah, please.
Is it visible?
All right. Okay. Yeah, it is. It is. Okay. Now, before you go to the surface, so the idea is, again, the most easiest way to understand these algorithms. Okay, let's just look at gradient descent and stochastic gradient descent. All right. There's a mini batch as well. I'm not going to talk about that. It's a marriage of convenience between the two in a way. Let's look at a simple univariate linear regression. So you have x's and y's. You're trying to fit a straight line. And when you do that, you determine a cost function. Now let's talk of the typical gradient descent cost function. So if you look at a typical gradient descent cost function, what you would do is, Kyle, in this case, what is your y? It is 10.49, 11.88. That's y, correct?
Yes, we see. That's
All
why.
right. Okay. So what are we doing here? We are estimating, since it's linear regression in one variable, I can say y is equal to w0 plus w1x. Let's say that's my function. And I'm trying to estimate the values of w0 and w1. So what I would do is I'll plug in the x values. In this case, I'll start with 1. I have an estimate of y. Then I have an actual value of y. I figure out the difference and square it. So the difference is basically the error. Think of that as an error term. Okay. Of course, here we are still estimating w0 and w1. We don't know what w0 and w1 is. So what you have, when you take the first data point and you square the error, you get a error function or cost function in w0 and w1. Okay, it's a quadratic convex function. Now you do that for each and every data point. So there are 5 data points here. So you have 5 such functions, and then you take an average of that. So if you look at the typical cost function, not typical, that's how it is. When you talk of, say, univariate linear regression, the cost function would look something like this. You would be summing up the squares of the actual value, which is 10.49, and the estimated value, and then you divide it by the number of data points here, which is 5, right? And what you do is you get, I mean, in this case, you get a surface, basically. So you start from a point, which means you start with a w0 and w1. And then you compute, I mean, you take the first derivative, partial derivative of the cost function. And then if you look at it, when you compute the derivative, in this particular case, you would do summation of 5 different there'll be 5 different computations that you have to do. When you update the weight, you have to do 5 computations before you update the weight. Because if you look at the cost function here, it is. Do you have an expression somewhere, Kyle, so that we can show that? Do you have it somewhere? An expression of the cost function for the gradient descent?
In the code, shall I
Not in
share
the code. Do you have the code where you have the expression for the cost function?
Yes, we see.
Or do you have it in the deck? What do you have in the deck? Can you
In
show me the deck? Show me the deck.
The PPT we see.
Yeah, please. The gradient descent one.
Only the definition.
All right. So this is not the batch. Is the batch the usual gradient descent, or is this?
Yes, we see. This is the traditional gradient descent.
All right. Okay. So, okay, so the way it works is you take all the, okay, imagine iteration as one. So the whole idea of gradient descent is you keep updating the weights to reach the minima, right? Now the question is, how many data points are you going to use before you start updating the weights? So if you look at the traditional gradient descent, we're calling it the batch gradient descent here. I'm not sure whether it's exactly the right term, but let's say it's the gradient descent, okay? What we'll do here is we'll take all the data points. If there are 100 data points available, you take all the 100 data points into your cost function, you compute the gradients, and then update the weight. So the next time you update the weight, you again have to take all the 100,000 data points, calculate the gradient again, plug in the revised weights. I mean, plug in the latest set of weights, whatever has to, I mean, not the latest set of weights. I think it'll be the Y, X and Y's or whatever, right? And then again, update the weight. So with each updation of the weight, you have to use all the data points. So just imagine there are 100,000 data points and you update the weights 100 times. So which means the number of operations that you have to do is 100,000 multiplied by 100. That's gradient descent. Now, evidently, it can be time consuming because, if you were to update weights so many times, then yes, it can be certainly time consuming. And so what we do is we come up with an approximation of doing the same process, but the reason why I'm calling, I don't want to call it an approximation. It is stochastic. I'll tell you what I mean by stochastic. So the word stochastic means random. So Kyle, can you go to the next slide, the stochastic one?
SVC. But before that, in in batch gradient only we'll be having less number of weight updation than stochastic.
How are you so? Okay, let's not come to that. The number of updations would depend upon how soon you converge, correct? It's always dependent on the convergence, right? So can we be certain that in the batch gradient descent, the number of updates will be less compared to the updates to weights will be less compared to stochastic? Can we say that?
But if you take for one epoch, we'll be updating 1,000 times in stochastic, but at batch gradient we'll be updating only once, right?
Yeah, in a way, yes, you're right. Okay, but I think that's not the point here. The point that we're trying to make is
The
do
reason
one
why the
single-
complexity varies is
Mhm.
because we'll be calculating the gradient for the entire data set at once in batch gradient. That's where we'll be computing more. But when it comes to stochastic, we'll be calculating the gradient for only one point at a time. Eventually, we'll be doing in both of the algorithms, for one epoch, we'll be handling all the data points, but in batch, we'll be handling entire data point at a time. So that would increase the
Okay, so
complexity or
okay,
cost.
let me, okay, I'll reserve that. Okay, but before that, let's differentiate between batch and stochastic. Okay, before we come to how many updates, etc. That's a different problem in itself. With stochastic gradient descent, what happens is I don't take every data point. I mean, I don't take all the data points, come up with a cost function, and then use that cost function to calculate a gradient and then update the weight. I don't do that. Instead, what I do is I randomly pick a point. It's random, which is why it's stochastic. Otherwise, there's no reason to call it stochastic. So if there are 1,000 data points, I'll pick one data point at random. For that data point, I can derive a cost function. Remember, when we do batch gradient descent, the cost function is you take all data points, square it. I mean, you take when I say square it, I mean the error is squared. But just imagine you have one data point and then you squaring the error, you'll still get a cost function. So for example, Kyle, can you just show that surface?
Yes, VC.
So for example, here, imagine this to be in the x-axis. I mean, in the x and the y-axis, you have two weights. So this is the cost function in the weight space. So you have W0 in one axis, W1 in the other axis, and let's say you have the cost function in the z-axis. You can have different cost functions for, I mean, each data point will have its own cost function in a way, right? So you're actually, I mean, when you do stochastic gradient descent, this is what you're dealing with. You're dealing with, depending upon the point that you choose, you're dealing with different cost functions. So the way it works is, Kyle, can you go back to the deck? The presentation. Thank you. So the way it works is you pick a point at random. You have a cost function. It's a cost function derived using only that particular point. Let's be very clear. I don't need the entire training data set to determine the cost function. But then for that cost function, we are calculating a gradient. I'm updating the weight. The next step is I pick another point at random. So it's like I've taken the first point, I have updated the weights, then I pick the next point at random, which is why it's stochastic. And for that point, I can again derive a cost function. And I'll use that cost function to calculate gradients. And again, I'll update the weight. Then I'll repeat, in the sense, I'll pick another point at random. And I'll continue to do this until, of course, we'll have some convergence logic where we say, okay, enough is enough. We have converged, whatever, right? So the advantage that I see is, I think Kyle has a different point of view. Weight updates happen very quickly here. In the case of gradient descent, there's a lot of computation that I have to do before I do my first weight update. Here, I do a weight update with very less number of data points. But of course, the problem that I see here is it's an approximation. The actual problem that I want to solve is the cost function of the cost function that we're using in the gradient descent. That's the actual problem that we want to solve. We want to minimize that. But computationally, that could be a costlier problem to solve, which is why I think we're using this where we're taking one data point each and solving the problem. But again, the problem that I see here is now the data point can be a freak data point, for instance. So Kyle, if you can just show me that surface, for instance. Can you go to that surface, the bunch of surfaces that you've drawn?
Yes, VC.
So, I mean, think of these surfaces as cost functions for each data point. Okay, so there are 5 data points here. These are cost functions. The average surface that you see on the screen, not very evident. It's apparently colored in red, sits somewhere within those surfaces. That's the cost function that we would be using for gradient descent. And that's the ideal thing we should have done. All right. But instead, what we do is we hop between one point to another. So when you hop between one point to another, what you're effectively doing is you're moving from one surface to another. So for example, if you pick a point at random, which is a freak point, which doesn't really quite fit into that, the line that you want to fit, then you might start with a cost function that is way beyond, the area within which you want to operate. Okay, so effectively what you're doing is, with every weight update, you're hopping between surfaces here. Whereas if you look at the gradient descent, it's one surface that you're dealing with, the average surface as I call it, and you're traversing the average surface to come to what is called as a minima. Here, what you're doing is you're hopping between these surfaces and try to, reach a minima. So that's, and finally, there is a compromise between gradient descent and stochastic gradient descent. So where you, instead of taking 1 point, just 1 point, so let's assume there are 100,000 points in, that you're dealing with. So if you were to do gradient descent, then for each weight update, you'll have to do calculations for all the 100,000 points before you do your first weight update. That's one extreme. The other extreme is where you deal with 1 point, which is stochastic gradient descent. Then you have a compromise here, which is the mini batch gradient descent, where you say, I will rather deal with batches of say 1,000, which means I would not go to the extreme of taking 100,000 data points before I compute the weight, or rather update the weight. And nor would I go to the extent where I will update the weights with each point. Instead, I'll take 1,000 data points. And for those 1,000 data points, I'll do the computation, basically figuring out the cost function, the derivative, the gradient, blah, 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 update the weight. Then I'll take another batch of 1,000, do the computations, and then update the weight. So that is called as mini batch gradient descent, which is a compromise between two extremes of gradient descent, or batched gradient descent, as Kyle had put on the deck, and the stochastic gradient descent. So this is our understanding, Bhargav.
We see, I have one more point why we choose SGD over GD for recommender system.
Go ahead.
Because in SGD, as you said, we need only a few points, or we'll be updating the weights a point after the point. But for GD, we need the entire data set. Since the recommender system is dynamic, we will not be getting all the data set in a time, right? So we cannot use gradient descent. So that's why we'll be choosing stochastic gradient descent over gradient descent, I think.
Okay. I'll leave it to Bhargav to evaluate you, because I'm not competent enough to evaluate your statement. Go ahead, Bhargav.
Give me 1 minute.
Sure.
I'm so sorry. Okay. No, I haven't thought about it, but Kyle's answer looks directionally correct. Well, I'll confirm and I'll let you know. Okay, so I have a deck. I'll walk you through some deck if it's okay. Can I?
Yep.
You all have a deck. I also have a deck. So okay. We figure out how to. There's a way to make this full screen. Yeah. Okay. Okay. ignore all of it. You guys know all of this. We'll talk about, this is like entirely on recommendation system, but we'll talk about some of these things later. I'll come back to you to all of this. Okay, so the things that you need to understand is that there are three things that matter in recommendation system. There are items. In here it could be movies. In e-commerce it's products. It could be anything. So there's a bunch of things that are called items, and there are users for whom the recommendation is the target. And there's a signal that everyone provides. Signal could be explicit or implicit. Super important to know. Your model that you build changes whether you're using implicit or explicit. I'm not sure if you covered this, but explicit, you explicitly give feedback, telling 1, 2, 3, 4, 5 is an explicit feedback. When you give it, you typically tend to do some kind of regression model. You can do implicit, telling you watched or not watched. Then you can do a binary or a multi-class classification model. So whether you build a regression model or a classification model, it's typically built on doing something on the kind of feedback, right? The kind of feedback is set up in a matrix, which is what we call as a rating matrix, right? So let's say that there's a bunch of items. So the items in this example, I'm taking the same example that you all picked, movies. So there's different kinds of movies: WALL-E, iRobot, Cars, Shrek, RoboCop, different kinds of movies. Now, Naveen made a good point, which I have to tell. I have nothing else. I want to make product prediction, which is typically the cold start problem, right? Cold start means that the user has just logged in. For example, I'm not even logged in. I'm just seeing what is happening. So for example, you go into an incognito mode in YouTube and open YouTube on a browser, it would still show you some videos, because it's not blank state is not useful for them. They need to show something when they start when a user is not logged in. At that point in time, one of the popular methodologies is the popularity based ones, which is the number of ratings, number of views that someone has watched is probably, or what is trending. You can come up with some popularity metric. Popularity could be trending, could be based on number of views. You can slice and dice. Somebody told some interesting thing, descriptive statistics. So it's all descriptive statistics. You slice, dice, get some metric, and then put it out there. That's what your base version when you start is. Then the second thing is you could have some additional information about every single thing. So the genre could be animation, sci-fi. You could have the total views. You can have IMDb ratings. You can have a bunch of these stuff. Now I can find my similarity between these columns, right? So if I want to do WALL-E versus Cars, I just need to find the similarity between these two. How would you do similarity measures? Did we cover this earlier? I don't remember.
No, we haven't. We haven't.
Okay, so I want someone.
But I think some of them know about cosine similarity.
Cosine similarity, yeah. So
Right.
maybe pick some data set and do cosine similarity is how you would do. You have two vectors, so you would. This is the label. These are numbers. So we know that this needs to be used, converted into one hot encoding or a label encoder, because we are doing cosine similarity. You have to use one hot encoding. Label encoding will mess this up. So you need to use one hot encoding, and then you put it into some cosine similarity, like SciPy. It's all like one line of code in whichever language that you use. But two columns you can use cosine similarity, and it'll give you a number. It's just cos theta. If the two things are similar, then they are close to each other. Cos theta is 1, cos 0 is 1. If they are far from each other, cos 90 is 0. So you know that if they are very far, they are not at all equal, then they are perpendicular, then they are orthogonal to each other, then it's 0. If they are similar to each other, then it's closer to 1. So you know the value. This is simple trigonometry equation that we use here, which is a content-based approach. So again, one was descriptive statistics, This is simple statistics that we use. Now we have this thing, which is what a lot of what we did today, which is that I have a bunch of users and I have a bunch of movies they've watched. I'm using watch history as one. We can now go and then we want to, let's ignore all of this additional information that's out there, which is what we want to do, right? So I have users and I can have user information because we have items information. Similarly, users can also have demographic information. I think Naveen brought this point. So people in India like this. So top 10 in Netflix, when you log top 10 trending movies in India right now. So that's all based on location. You can start doing some of these things. Some basic levels of personalization based on their specific watch history. Or so for example, in India, someone has watched an animation. So this is again descriptive statistics, but clearly you know why that is happening. Why are we doing something like this? Is I will have, which I didn't talk about, but your recommendation system you need to build trust, you need to build engagement, you need to introduce serendipity, people need to take confidence in what you're building. All of these things are extremely important metrics when you do recommendation system. So there are various ways in which when you go into your, how do you design your API and put it into production, there's a bunch of these things that are super important when it comes into place, not so much just the models alone. Operationalizing is a nightmare, is as equal a nightmare as building the models are. But I'll stick to the models here. So, which is what we discussed here today, right? So we're going to convert this into two matrices. So you have two matrices here. So this is like 1, 2, 3, 4, 5, 1, 2, 3, 4. So this is 4 cross 5. So I'm taking two latent factors. The way it works exactly as VC explained. VC explained it really well. We take some random numbers and then we multiply it only for the numbers that are here. We find what the difference is and then we try to minimize it because we need to keep changing these numbers to ensure that they're as close to ones as possible. Once we have it, we multiply, we can fill out the entire matrix, and then now we know that for Ella, what is the one that we need to recommend. For Beam, we know what we need to recommend because that's the highest number that we know that as part of it is what we are doing. This is user item. So given users, I'm going to recommend item, right? Based on all the users that we have seen, users similar to them who have similar watch history have watched this movie, and so this user would also be interested in watching something like this. That's what collaborative filtering would do, right? But we need not, but we need not stop here. We can go into, so you would now hear about deep content filtering, deep learning based models, which will all include a way where we can also add age, location. So we can add information about them and we can add information about users and items. And then we can build models, which is all embeddings. We'll do some of these things later on when we do a bit more into these models. But just remember that in the current state of art, you would build a baseline model quickly using, we would do everything that was done before, but you would also add another layer of doing deep learning based models. I'm trying to see if there's anything else that I want. This is all okay. This is okay. No, these are all like operationalizing stuff. But that's something that you need to understand when you want to put something in production. Remember that item would be done using cosine similarities because two items, how close they are. User item would be done through collaborative filtering, and user is typically not done because that's not a meaningful item, because unless you're in this matchmaking business of Tinder or Bumble where you need to recommend another user, you would never have, in which sense, unfortunately, for the name of nomenclature, everyone becomes an item there. So it becomes like, it's very unfortunate, but that's how it's modeled. But those are the ways. You would never do a user. I think I saw in chat also, is there some kind of clustering? So that's not typically the approach that we would follow. That's all an internal thing. You would only use cosine similarity, if you can take away telling that, oh, I can do cosine similarity or I can do collaborative filtering, and cosine similarity is simple statistics, just finding the cos angle between two vectors versus matrix factorization for collaborative filtering, you're already really good in recommendation system. When we do a bit more deep learning, we'll do one use case on how we would use a deep content recommendation for deep content filtering, deep collaborative filtering for recommendation. Like we'll talk a bit more about newer architectures on how Instagram and YouTube create recommendation systems. But we'll do this in one of the subsequent sessions. We'll move away from recommendation system soon, but we'll come back to it when we do more deep learning. Questions? I mean, I just summarized everything. You've already seen all of it, but
No, but question, did we get gradient descent and stochastic gradient descent right?
I mean, the explanation is all correct. The explanation is correct.
All right.
Yeah. Perfect.
We see and all, like Bhargav is well known for recommendation system. Between 2014 to 18, I guess, is one of the best.
Oh, that's he's.
Not in the country, in the world.
Do we have Vidya here? Or we have it? Bhargav, you should announce her internship. If you don't mind. You should, right? She's starting, right?
Yeah, she joins us. She herself is.
Yeah, I'm here.
today.
I'm here. Yeah. Hi.
So why don't you just announce it to the group so that Amma Makkal?
I'll post it. Yeah, excited to have Vidya on board working with us.
Thank you so
starting today.
much. Yeah. Thank you so much for the opportunity. Yeah.
So you're going to intern with 5C, is it?
Yeah.
Yep.
Okay, wonderful. But build models for them.
Yeah. I'm learning and yeah, I think it's a very great learning opportunity. Like I'm really impressed. I actually missed the 2 sessions. I'm just trying to catch up. And it's really interesting to see. Yeah.
You're picking up the nice words, the right words. Corporate style.
Like more like it's interesting. Like nowadays I feel like I have some purpose. Like when I see like recently, like my daughter is home now and she was asking like, yeah, I see Netflix and they say like this is what. So I feel like happy to explain it to her. This is what I'm working on. So that really excites me, you know. Yeah.
All right. Wonderful.
Nice. That's wonderful.
Yeah.
All
Give
right.
heads up. Manan is listening to this conversation. We should
Srisha dropped. I didn't know when she dropped.
No, she's there. She's there. It's just that her video is not switched on.
Oh, she comes with a different name today. Oh, I didn't know that. Okay.
She comes with her original name, Sai Sirisha Meduri.
Understood.
All right. So Bhargav, what do we do on Wednesday? We haven't discussed it yet, but any thoughts?
If you're up for it, I want to do one session on. Did I give you a list of topics on calculus that needs
You
to be
did. No, we didn't complete linear algebra. Can I continue with linear algebra? Because I still want to. No, not worth it, is it?
What? So you've done.
I haven't done independence yet. I'm still. We're still, just to keep the group bit engaged and not to throw a lot of math at them.
At some point, they would have to go and do it themselves. I think we'll do one calculus and then move to. I want to do tree-based models. We haven't done tree-based models.
Decision tree.
Decision tree, random forest, gradient boosting. I want to do that. So if you can do one session of calculus, then we'll go and do tree-based models. They will all be done in one session.
Tree plus calculus, is it?
No. Calculus is one session.
Okay.
Tree-based models is another session.
Okay. Let me see, because I also have to pick it up. It's my
I
calculus is
think
also
I
a bit
gave you,
rusty.
I think I've
Yeah,
already given you the
yeah,
list
you
of
did. You did.
top things. Those like those are enough. That's enough.
Hessians and Jacobians and
Yeah, Hessians, Jacobians, and if you can do a slope, I think slope tangent. I mean, okay, tangent, and then area under the curve. So integration. So this is all differentiation, and then one on integration. That should be enough.
Okay, let me work on it. Sure.
Okay. If it's not, I can do. Yeah, let me know. If it's not, then we'll do tree-based models on Wednesday, and then we'll do calculus on Friday.
Do you have some content for tree-based models at deck
No, I'll wing it.
Okay, cool. Just get ready, just in case I'm not ready with calculus on Wednesday.
I can do it any day.
All right, cool then. Then it's okay.
I'll be there in my deck. I have my deck is open. I'll have some version of it.
All right, cool.
Yeah, the deck I showed today was I built in 2016.
I still remember.
Yeah. Done.
Any questions, folks? Those on the call?
Also, we see like on logistic regression, we
Still
have some.
pending. But let's do a little bit of probability, because it's isn't it closely tied to probability, right? The way logistic regression works. So Bhargav, on his list, he had some probability, of course, calculus and probability. So let's do some probability so that people understand what's conditional probability is, for instance. I think that's important.
Very important. Right? Conditional probability is important.
It's extremely important. So let's do some calculus, some probability, and then when we move to logistic regression, I think people will have some idea of what we're talking about.
Yep.
Others on the call, any questions? Folks, just one thing, strong recommendation, unless you get your hands dirty, all this will go right through the roof. I can tell you that. Even to get gradient descent and stochastic gradient descent right, I mean, Bhargav said it's right, so I believe it's right. Me, Sandhya, and Arun also joined yesterday, and we had Kyle Viri. I got it wrong, to be honest. It was Kyle who corrected me. Then I thought about it, and then I realized that, okay, she's right. So, I mean, unless you start thinking about it a little deeply, you're probably mugging up the way you're mugging up stuff for your exams. So, strong recommendation, think about these problems a little more deeply. You will not get it. Please post questions in the group or ask in one of our calls. That's the only way to, take it forward. Otherwise, this is just like any other class that you attend at college. And Bhargav, I still didn't get, I played God and then I came up with those factors.
I didn't understand your question. Can you?
Yeah, so the question was, just imagine, again, take the, the users matrix and then the user movie matrix. And let's say I play God and I decided the world comprises of 3 kinds of people and 3 kinds of movies: action, comedy, and romance. Then what I do is I have 5 people and I say, one person is 0.1 times action plus 0.3 times blah, 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 plus whatever. The sum of that is 1, by the way, right? Likewise, I designate the movies.
Why is sum of that is 1?
No, not necessarily. Just it turned out. It doesn't have to be. Okay. I think. Okay. Let's say it's 1, just for the sake of.
Sure.
Let's say normalizing, if I may say so. All right. Then what I do is, assuming, and if I. Then the next step is I come up with a ratings matrix now. How do I do that? I basically do a dot product of the users. So these are in a way latent factors, just that God-given latent factors. Look at it that way, right? And I come up with this ratings matrix. So what I do next? Of course, I'm not doing any predictions here. So the ratings matrix is dense, nothing sparse about it. I run it through a typical SVD algorithm or PCA SVD, whatever. Let's say it's SVD, right? Now, what SVD did was it did manage to identify 3 latent factors. It did. 3 were dominating, no doubt. And the 3 were dominating. So I constructed the P, the other one, the Q transpose, and then the eigenvalues matrix, the square root of eigenvalue matrix, right? So if I combine the 3 matrices together, multiply them, I do get the rating, not a problem. But I know I'm not getting it, because if you look at the, if you take the P matrix, for instance, each vector, each row is, I believe, orthonormal with each other. I think so. So if I take the dot product of each row, I should get 0 if I'm right. But I get some of them are negative, some of them are positive, so on and so forth. But what I don't get is, I don't get the ratio in which I mixed. You remember when I started the story, I played God, and I mixed. When I took a particular person, let's say Vijay, I constructed Vijay as 0.1 times action, plus say 0.3 times comedy, plus say 0.6 times romance. Of course, that doesn't define me, but still. That's how God, let's say, designed me. But it determined the latent factors, 3 latent factors, but the weights were, the factor weights were weird. It didn't reflect how I chose to, create Vijay or a movie. And though when you multiply, do the dot product, the ratings were right. So my question is there a way to get to those weights that I used to, combine these God-given latent factors? Is there a way to get to that?
You want to do if we can reconstruct it. Wow. Didn't think about it. Okay, now I understand the question. I don't have an answer. Let me think about this. I really don't have an answer.
Right. Okay. Because otherwise, I'm just wondering, what do those weights mean intuitively? Forget how I constructed the, how the linear combination that I used to construct each individual and movies. Okay, let's leave that aside. Okay. When we run SVD on the matrix, ratings matrix, it did give me 3 latent factors, no problems. It does give me some weights for each of those latent factors, right? Factor loadings or whatever you want to call it. And likewise, it gives us 3 different, it gives weights for the movies as well. Now, some of them are negative, positive, you take the dot product and blah, 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 and all that is fine. But what does that negative number mean? If you think about it, my choice of a movie there's no negative weight associated with that. So I'm just wondering, what does that negative mean? Is there a way to even normalize it?
In some sense, you have touched a very raw nerve. Explainability is a big challenge in machine learning, right? Because this is latent factors, right? You knew what those factors are, but you couldn't reverse engineer because you knew the axis, the scale in which you are measuring, and it was transformed into another axis where you're unable to reconcile and figure out what it is, right?
That is right.
So I'm able to understand that, but I don't know how to make it happen, because I also don't understand. I haven't done enough thinking on how to represent.
But is it the beauty of dot product? Does that actually symbolize the beauty of dot product?
It's also that it's.
No, I'll tell you why I'm saying that. If you think about it, we did the SVD algorithm. The dot product gave the same number.
Hmm.
Think about it, right?
Interesting.
In the God-given world, I had my own factor loadings. I did a
Mhm.
dot product, I got a number, right? Now this is a new world, an entirely new dimension. The dot product remains the same,
Wow.
right?
Fascinating.
Isn't it? So is that something beautiful about dot products there? I'm just thinking now that I think
Probably,
deeply
I
about
don't
it,
even know what it means, but yeah,
right?
nice.
Anyway, so that was a question that I had posed in the group. Is there a way
Hmm.
to? I know you can't get to that. That's my sense now, but I think there is something about that dot product which is really
Sure.
interesting.
Mhm. I'll think about this. I don't have an
Okay,
answer
sure,
right
sure,
now.
no problem. I'll also think little deeply.
Hmm.
The more linear algebra I learn, hopefully, I'll get a
Hmm.
hang of what's happening. Anyways, others on the call, questions? I know it's already close to 1. I'm still awake. I had my cup of tea.
Oh my God. Don't you have your yoga class in the morning?
Yes. 5.
Wow.
All right, folks. If there isn't anything else, that's it for the day. Anything else from others? Bhargav, anyone else?
Oh, I think I want to ensure everyone practices prompt engineering. If you don't, it's not a skill you will develop, right? Because we have moved far away into the wild world of math, but also remember that English is the most potent programming language right now. So please practice prompts, writing prompts, get good at it.
All right. If there's nothing else, then we'll call it a day.
See
Okay.
you.
Thank you.
See
See
you
you,
next
folks.
class.
Bye.
Everyone, bye-bye.